Good morning, physics fans. How we doing on this fine Wednesday morning? It is Wednesday morning. Yes, it's tough keeping track of the days, I know. But it is Wednesday morning. I hope everything's going well with you and your family. Hope everybody's staying illness free. Once again, continue to keep up with the material. Continue to do the little evaluation, self-check evaluations at the end of the notes. That gives me record of that you are participating and be a part of the class. Which once again now goes in as part of the class. Today we're going to talk about heat of fusion, heat of vaporization. We talked about heat of fusion and heat of vaporization. How do things melt? How do they vaporize? Okay, what is the process that goes about vaporization and fusion? Well, when you're talking about fusion, we talk about solids to begin with. Solids, they have bonds that hold the molecules in a fixed location. You have bonds that you have the molecules in here that have the bonds, and this is all chemistry, the ionic, covalent, whatever, the bonds that you have in here. They hold all these molecules in the fixed space. Okay, this is fixed. You don't see anything jumping out at what we have here. So there's bonds that hold the molecules in a fixed space, in a fixed location. As thermal energy is added to the solid, potential energy increases. Okay, what you have is sort of like a rubber band. Okay, and you're going to start getting more and more potential energy, and you get more energy stored in these molecules. And this rubber band is holding them together. That's like the bond that's there. You're holding it together, okay? It increases to a point where the bonds can't hold the molecules fixed together anymore. So it keeps on wanting to stretch because it's getting more and more energy, and you get more and more antsy and anxious there, and finally they break apart, okay? That is what happens when you have a solid that you increase the thermal energy for, which is the potential energy that you have there. Okay, you're not increasing the temperature at all. All the thermal energy goes into potential energy, and it keeps on wanting to stretch, and eventually they break apart. Okay, so the molecules can't be held in a fixed position anymore. At this point, the solid becomes a liquid. Okay? All of a sudden, these molecules have more movement that they can move around. They become more liquid, they become more fluid. They're not in the fixed position. During the process, the potential energy is increased, not the kinetic energy. The potential energy is increased, not the kinetic energy. Once again, you have these bonds that they're here. They're wanting to go out. They want it to break. So they have this potential energy. Once they break, now all of a sudden they assume a little bit more kinetic energy. During the process, potential energy is increased, not the kinetic energy. If the kinetic energy is not increased, then the temperature does not increase. Okay, once again, the average kinetic energy is proportional to the temperature. So during the process, the potential energy is increased, not the kinetic energy. If the kinetic energy was increasing, that means the average kinetic energy would increase, and then you would have a temperature increase. So what happens here is ice at 0 degrees Celsius, turns into water at 0 degrees Celsius. Ice at 0 degrees Celsius turns into water at 0 degrees Celsius. So once again, if we take a look at the beaker here, okay, we're at 19 degrees Celsius in the beaker, and I'm going to throw some ice cubes in this beaker. Okay, these ice cubes are solid. They have fixed positions. Okay, well, what's going to happen is they're going to eventually melt because we're at 19 degrees Celsius in the beaker with the water. Okay, which is the room temperature. Okay, and the ice cubes are now starting to melt within the beaker. Okay, what is happening is the potential energy is increasing, and the bonds at the surface, remember what we talked about yesterday, how things heat and how things cool down, okay, the bonds at the surface start gaining potential energy. Eventually, they become fluid, they break the bonds, and then the next layer of bonds will start to decrease or be broken, and the next layer will be broken, and the next layer will be broken. And eventually what happens is the ice cubes will melt. Okay? Their potential energy turns into kinetic energy, or the potential energy, the thermal energy that's receiving is all potential energy which breaks the bonds. Okay? But once again, all the thermal energy is used to increase the potential energy to break these bonds. So the bonds at the surface of the ice cubes here, the bonds at the surface of the ice cubes are the ones that are broken first. And then the next level, and then the next level, and then the next level. Where eventually, all this ice at 0 degrees Celsius will turn into water at 0 degrees Celsius, and then start mixing with the temperature or with the water that's already in here that started out at 19 degrees Celsius. Okay, the ice cubes have now been melted, and the temperature is now down to 16 degrees Celsius. So you have water, you have ice at 0 degrees Celsius. So we had ice, some ice cubes in here at 0 degrees Celsius, and then we have this water level that was at 19 degrees Celsius. This was at 0 degrees Celsius. The 0 degrees Celsius ice turns into water at 0 degrees Celsius and then starts mixing with this 19 degrees Celsius water. So what you have is you have a solution of 0 degrees Celsius water and 19 degrees Celsius water. They want to try to achieve thermal equilibrium. They'll try to achieve this thermal equilibrium. And that thermal equilibrium, when we mix this all solution together, turns into a 16-degree solution. So this ends up at 16 degrees Celsius because we mix 0 degrees Celsius with 19 degrees Celsius. The mix will give you a 16 degrees Celsius solution. That's what happens when you put ice in a glass of water to cool it down, or a glass of pop, or in a Gatorade. You pour warm Gatorade over some ice. The ice melts. The ice melts, turns into 0 degree water, and it mixes a solution with whatever the temperature of the liquid is that you're pouring over it. But once again, the process is thermal energy is used to increase the potential energy to break these bonds. Once you break the bonds, then they become more fluid. Heat of fusion. When you talk about the heat of fusion, it's the amount of energy required to melt a mass of a solid. Okay, this is sometimes referred to as a latent heat of fusion. Okay, so we have the latent heat of fusion. Okay, so the heat of fusion is the amount of energy required. How much energy do I have to add to a system to be able to break these bonds? Okay, to change a solid into a liquid. Your units are joules per kilogram. Remember, energy is measured in joules. So we have joules per kilogram. And if we look at ice, to go from ice to water, it takes 3.34 times 10 to the 5th joules for every kilogram to melt. Okay, so that's a lot of energy per 1 kilogram to melt. This means it's 3.34 times 10 to the 5th joules of heat is needed to melt 1 kilogram of ice. And once again, just think about this. When you have ice, if you have 5 kilograms of ice at 0 degrees Celsius, now ice could be less than 0 degrees Celsius. Okay, it depends on what the temperature of the freezer is. So it does not have to be exactly 0 degrees Celsius that it starts out at. So ice could start at 5 below 0 or 10 below 0 and then work its way up to 0 degrees Celsius. But ice at 0 degrees Celsius turns into water at 0 degrees Celsius. So 5 kilograms of ice turns into 5 kilograms of water, and that water becomes 0 degrees Celsius, and then it starts mixing with the other liquid that you're trying to cool down. The energy added only changes the state, not the temperature. It changes the state, not the temperature. So when you add the energy, it breaks the bonds. All that energy just goes into breaking the state, or breaking the bonds, which means it changes the state. So once again, 5 kilograms of ice at 0 degrees Celsius turns into 5 kilograms of water at 0 degrees Celsius. Energy added only changes the state, not the temperature. In the state, this energy is used to break the bonds. When you break these bonds, you change the state, whether it's solid to a liquid, or a liquid to a gas. So you're changing a state, and the temperature stays the same of whatever you have. We have heat or vaporization. If I'm going too fast, once again, just hit the pause button. Heat or vaporization is the amount of thermal energy required to vaporize a mass of liquid. So now when we talk about vaporization, now you're boiling water. Okay? It sometimes is referred to as, once again, the latent heat of vaporization. Now, for water, once again, you have 2.26 times 10 to the 6 joules per kilogram. It takes more energy to vaporize than it does to liquefy. Okay, we can melt it a lot easier than it takes to look to vaporization. Just because, think about your environment. I can set an ice cube somewhere and I can melt it real quickly, just by the amount of energy that's out there. But that water doesn't easily evaporate. Okay, it takes a longer time for it to evaporate. Eventually, if you have some water on a countertop somewhere, eventually it will evaporate. Okay, the rain that you have out here on the cement, eventually it evaporates out there. Now this amount of heat, the amount of heat, this Q, is the amount of heat required to melt a mass M. Okay, this Q variable, we use that as our heat. It's the amount of heat required to melt a mass of M. And the amount, to calculate this, we have our heat of fusion times our mass. And likewise, QV is the amount of heat required to vaporize a mass M. And every solid has a heat of fusion. Every liquid has a heat of vaporization. Okay, so we just put the water up here, but you can find tables, and I'll give you, I can maybe find a table also, give you a table once we start using other masses, other types of masses, because what we'll do is we'll look to cool down with water. We'll look to cool down in the water some mass. The ice cubes get cooled down in the water, but if you have steel or if you have copper and you try to cool that down, there's a little bit different things that we have to use in regards to that. And we'll talk about that tomorrow. But what we're just talking about today is changing a state. And when you change a state, it requires heat to be able to change a state. Okay, it takes energy. And that energy is thermal energy that turns into potential energy, which once again allows the bonds to break at that point. Once they break, they can now start having a little bit more fluidity and they can start moving around a little bit more. But here, when it's in a solid state, they are stuck right here. Can't move. They'll vibrate a little bit back and forth, but that's it. But the potential energy, as you add the thermal energy, will continue to increase this potential energy to where they will eventually break, and then they can start moving around a little bit more. Okay, the amount of heat required to melt is the heat of fusion. You have the heat of fusion times the mass, and then heat of vaporization times the mass to find the amount to vaporize. We take the water and we vaporize it into the atmosphere at that point. That is heat of fusion, heat of vaporization. Tomorrow we'll come in, we'll talk about specific heat, and we'll talk about how objects cool down and how much heat is required to cool down or to heat up an object. We'll talk about that. That will be tomorrow with the idea of specific heat. Please do answer the questions at the end of the notes here. We'll try to get some, like I said, this is sort of you being able to interact a little bit with me and me to get some evaluations in regards to this. Once again, we have 2 chapters left. We have this chapter we go through, and then we have one more chapter we're going to go through also that talks about thermodynamics, and that will be pretty much it for the school year at that point. If you have any questions, feel free to ask. You can comment it. That is fine. Send me an email. That is fine. I'll get the message and eventually get you an answer to it. Other than that, I have nothing else for you. Thinking, no, I have nothing else for you. I miss you guys. I wish you were here in class. But this is our normal, and this is what we're at right now. So please take care of yourself. Hopefully everybody in your family is doing well. Please take care of yourself. Keep your social distancing out there. And once again, let's do our part to be able to get ourselves back to some sort of normal. Other than that, I have nothing else for you. Enjoy your day. Yeah, rained a little bit this morning, but they say it's supposed to clear out a little bit now and be warm, so that would be good. Enjoy your day. I miss you guys. Adios. We'll see ya.